Hello! In this demonstration, we'll present how Parasoft C++ Test CT helps improve code quality and streamlines compliance with functional safety and process standards. C++ Test CT is a lightweight, command-line-oriented tool for C and C++ code dynamic testing. In between other features, it supports collecting multiple code coverage metrics from various testing practices and generating traceability reports from unit test execution. It's designed for automation and CI integrations and comes with an excellent VS Code extension. C++ Test CT simplifies achieving safety standards, goals, and objectives. Some examples of the standards are ISO 26262, IEC 61508, IEC 62304, or DO 178C. Unit testing, requirements-based testing, statement, branch, and MCDC code coverage reports are all essential requirements from these standards. In our demonstration, we'll show how to provide evidence for achieving code coverage goals from GoogleTest-based unit testing and how to use GoogleTest cases for requirements testing. In our demo setup, we will use a popular combination of technologies. GitHub is our CI platform. Developers use VS Code for coding and GoogleTest for unit testing. Our toolchain is fully Dockerized and it includes CMake, Ninja, GCC compiler, and of course C++ Test CT. The use of containers ensures ease of infrastructure instantiation and consistency between developers' desktops and CI. Our development process is based on the CI workflow. In our demonstration, we'll see an example of the workflow with testing for compliance. Our focus will be on unit testing and code coverage, but this kind of workflows almost always include static analysis and coding standards compliance. In our demo, we'll go through the following sequence. We will start working on a new code in a dedicated feature branch. The code will be developed according to requirements defined in Jira. Implementation will be tested locally at the developer's desktop using GoogleTest and the containerized toolchain. In the next step, the developer will create a pull request. The pull request will trigger a pipeline with an automated quality and compliance gate, which includes more extensive testing than developers can perform on their desktops. The pull request will fail in our demonstration due to insufficient MCDC coverage. Pipeline's execution reports will be published on GitHub pages, and after a quick analysis of the report published on GitHub pages, the developer will download pipeline results to local VS Code and use extended reporting features to save time developing missing test cases. After fixing all issues, the developer will push the code back to GitHub and the pipeline will be re-executed. The quality and compliance gate will open this time and the developer will merge the code with the main branch. The merge operation will trigger another pipeline that monitors the state of the stable stream. The results of this pipeline will be sent to Parasoft DTP, a web-based reporting system that aggregates the testing data, generates compliance reports, and visualizes testing results with graphs and trends. Let's switch now to our demonstration environment. Our demo project is based on a popular open source library for inter-process communication. In our design, we plan to use it in the autonomous driving system. Our project is hosted in GitHub and team uses a modern CI-based development workflow with containerized toolchain and automated CI quality gates. For our code, we need ISO 26262 AZD compliance. So far in the early stage, project was developed with limited attention to standards compliance. This frequently happens when internal company components developed without standards compliance or open source modules are mixed into a safety critical system. In our situation, we plan to certify adopted open source module, which was internally extended with new functionalities. So far, when working on the project, developers used GoogleTest for unit testing, but the process has not been systematic. Testing was not traced to requirements, and code coverage was monitored only for line metric, which is not sufficient for functional safety. The investment in creating Google test cases is already significant, so we want to use them for certification and save our team's effort on rewriting these tests to a proprietary framework. For our next compliance milestone, we have two goals. We want to start monitoring statement and MCDC code coverage for the newly created code, and we want to start tracing relevant tests to requirements. With Parasoft C++ Test CT, integrating code coverage into project builds is easy. There are dedicated integration packages for build systems such as CMake or Bazel. The tool is also very easy for containerization. To integrate the tool for our demo project, we need one small insertion in the CMake list file and a corresponding configuration file. With this change, our build targets are extended with code coverage monitoring, and we can move on to implementing new features. So let's say our task is implementing the emplace method for a vector class. We do have a set of low-level requirements for this functionality. As a developer, I've analyzed the specification and implemented the first version of the emplace method. I've also added the first couple of unit test cases. Please note that my test cases are correlated with requirements via dedicated properties injected into test cases. This correlation establishes a test to requirement link that enables C++ Test CT to generate requirements traceability reports mandated by all safety standards. Now, I'm interested in whether my tests pass and the code coverage level for my newly implemented code. Let me build the project, run new tests, and generate code coverage reports. As you can see, the code was built and tests were executed. As a part of the build process, C++ Test CT generated code coverage reports. CT generates reports in multiple formats, including raw text, machine processing friendly JSON, and HTML. For developers, the VS Code extension is probably the most convenient way to analyze the results. Let's enable line coverage and look at the new code we just added. As we can see, we do have some code coverage, but our basic tests examined only a part of the implementation. We need to add more test cases. We can derive additional test cases by requirements analysis. Let's add a few more tests, ensuring they are linked to appropriate requirements, and execute them. We expect coverage for the emplace method to increase. And indeed, it seems we now have 100% line code coverage. We are now ready to push the new code to the repository and create a pull request. My pull request triggered the automated pipeline. The pipeline goes through several stages, including code coverage quality gates. Let's take a look at our pipeline definition file while it executes. What we are looking at now is the YAML file that defines a GitHub workflow. Workflows contains jobs and steps that are executed on runners. C++ Test CT Lite command line interface and build system integration packages make it very easy to integrate into workflows. Here, the code coverage tool is injected into the CMake build. Build integration extends existing targets with code coverage and adds new targets for report generation. Our project default target includes building GoogleTest. Here we execute binaries with unit tests, and here we invoke reporting targets added by the C++ Test CT CMake extension. Once the report is generated, it's published to the GitHub pages so that the team can easily access it. Below are quality gates for coverage metrics. Our current requirements for the quality gates are 100% statement and 90% MCDC code coverage for the new code. The values are set with helper variables. Let's go back to our pull request and see the pipeline results. Our pipeline has failed. It seems we have a problem with MCDC coverage. Our line coverage quality gate passed, but the MCDC quality gate has failed. We simply did not achieve expected 90% of MCDC coverage for the new code. To understand the gaps, we can review the HTML report published on GitHub. The report contains complete results for all metrics, including details for MCDC or simple condition coverage metrics. The result summary table has configurable thresholds to indicate with colors results that may require attention, and covered code constructs are marked with highlights. Different types of results decorations simplify quick reviews and deeper dives required for a complete understanding. HTML report published to GitHub or GitLab pages may be a convenient way for a team to get an overview of the coverage levels after pipeline execution. For fixing the code, adding new test cases, and improving coverage, it may be more convenient for developers to view results using the VS Code extension. The C++ Test CT VS Code extension integrates with GitHub and enables downloading pipeline results to the local VS Code and viewing results without executing code locally, which is a huge time saver. We can now analyze why our MCDC coverage quality gate failed. Let's see MCDC results for the method we are implementing. We have 3 decisions in the method. For 2 of them, we have achieved 100% MCDC code coverage. However, we still don't have the complete MCDC coverage for the first decision. Let's take a closer look. C++ Test CT provides extended MCDC coverage reporting that helps understand coverage gaps. Diagnosing missing coverage can be a time-consuming task, especially for MCDC. This extended reporting provides easy-to-understand visualization of MCDC coverage and instructions how to add minimal number of test cases to achieve coverage goals. In our situation, we have 3 conditions in the decision. The second and third conditions are already covered according to MCDC requirements. We still don't have the coverage for the first condition. Here we have a list of test vectors that were executed. Table includes information about the values that conditions were evaluated to and the outcome of the entire decision. Below, we have the information about missing test vectors. A great value is that the tool computes the minimal set of the test vectors required for the complete coverage, helping developers to be more productive. In our case, we need a test vector to evaluate the first condition as true. It means we need a test case that tries to emplace an object at the position exceeding current capacity. Let's add this test case. In general, depending on the situation, different actions may be required to eliminate the coverage gaps, including changes in implementation, modification of requirements, and the addition of missing tests. In our case, the code was correctly implemented, following requirements, but the developer forgot to add a test case for a specific scenario. The problem was detected thanks to the C++ test CT based quality gate. Let's make sure our new test case is correlated with appropriate requirement, and now we are ready to push the code again. Let's add a comment. Alright, this operation triggered a pipeline for our pull request. Let's give it a minute to finish. Alright, it seems our coverage quality gate passed, and we are now ready to merge the code into master. For the master branch, we have a dedicated pipeline verifying integrated code. That's a different pipeline than the one executed for pull requests. This pipeline executes extensive set of tests and monitors the code coverage for the entire project. Our merge operation triggered this pipeline. The results of this pipeline represent the current status of our stable branch. Our pipeline sends these results to Parasoft DTP, the reporting platform. Parasoft DTP aggregates inputs from different types of testing and presents results in graphs, trends, and compliance reports. With these widgets, I can monitor my progress in various compliance aspects, including the progress with the code coverage. I can also check the progress with requirements implementation and testing. With this widget here, I get information about the number of requirements already covered with test cases and those that are not and require attention. This information allows me to react if my progress with compliance goals, including code coverage, is too slow. Unlike the point reports published to GitHub pages, which are useful for assessing the health of recent commits, DTP provides more in-depth analysis, including history and trends, and enables decisions regarding resource allocation and development process optimization. This kind of insight is essential for any persona involved in the safety, security, or quality process management. And this is the end of our demonstration. Let's recap. We went through a typical development workflow. A new functionality was coded in the dedicated branch. Implementation and testing were driven by requirements stored in Jira. For the new code, a pull request was created, which failed due to insufficient MCDC coverage. Developer used VS Code for accessing pipeline's results to understand the problem and fix it. Corrected code was pushed to repository. The second pipeline was successful and the pull request was merged. Push to the stable branch triggered another pipeline. The pipeline results were sent to DTP for trends and compliance reports analysis. In our demonstration, we focus only on unit testing and code coverage, but static analysis with MISRA or other coding standard could be implemented in the same way with Parasoft tools. In our demo, we extended the typical development workflow with compliance testing without reinventing the pipelines or changing existing development patterns. Integration with the existing CMake build was trivial thanks to a dedicated integration package. Developers didn't need to learn a new framework or rewrite existing Google test cases. All these aspects of software testing influence the certification cost. The overall cost also includes toolchain maintenance, which may be significant in the case of open source tools. Any problems in the toolchain may affect certification deadlines if we don't have a vendor behind that can react to a bug. The complete cost and effort analysis is not possible without knowing project-specific details. It is possible, however, to indicate where significant differences are. The important factors include cost of acquiring the toolchain. Here, open source tools look better than commercial products. However, when we add the maintenance cost, the situation is different because of the risk related to not having a vendor behind the tool. With open source tools, the qualification effort tends to be significant and may distract the team from their core activities. Commercial products are typically pre-certified, which reduces the overhead on the qualification. Another factor is the cost of integrating the toolchain into automated workflows. Here, solutions that depend on IDE or heavy GUI interfaces, like old-style unit testing tools, are definitely more expensive to integrate. And then we have cost components that scale with the size of the team and project. Commercial products based on proprietary testing frameworks require training for the entire team, which consumes a lot of time and causes distraction. Open source tools and frameworks are known by developers and typically do not require training. The cost of creating new test cases depends on the framework and team's proficiency in using the framework. Some of the commercial solutions use GUI-based test cases editors and proprietary scripts for defining test cases. These kind of tools sometimes enable test creation without coding skills, but when used by developers are visibly slower. Dev teams make the fastest progress when using popular open source frameworks such as GTest or commercial tools that utilize GTest. Teams that consider using a proprietary unit testing framework must also consider the cost of migrating already created Google test cases to the new framework. The cost here is proportional to the number of test cases and in many cases can be prohibitive. With Parasoft C++ Test CT, this cost does not exist. And finally, we have a cost of achieving coverage goals. With open source toolchains, teams get only a basic coverage reports without any additional hints how to create test cases that achieve higher coverage. This is especially relevant for MCDC coverage, which is challenging for non-trivial code. C++ Test CT provides here a great value by extending reports with additional hints that highly simplify missing test cases creation, reducing the overall cost of achieving coverage goals. As we mentioned earlier, the complete cost analysis depends on project-specific aspects, but the factors we listed here are among the most important. And this concludes our presentation.